Alright, so in this example, we are asked to solve a logarithmic equation, and it's a pretty difficult logarithmic equation. And the biggest reason is because we've got some addition going on. If we didn't have any addition, and I'm just going to make up a new one on the fly, imagine we had just one term, something like log base 2 of x plus 3 equals 4. Imagine that it was just this part equaled 4, and we didn't have this addition and that second term in there. Well, then life is good. If we have a single logarithmic expression, we can just change this into an exponential expression and write this as 2 to the 4th, which is just a number, well, and it's 16, equals x plus 3. Right? 16 equals x plus 3, and we're ready to solve. Life is good. We can just subtract 3 from both sides, and we find that the value of x that makes that statement true is 13. We can even check our work. Right? We can say, well, is it the case that log base 2 of 13 plus 3, does that equal 4? And we say, well, is log base 2 of 16 4? Is it the case that 2 to the 4th equals 16? It absolutely does. So, if we had just one simple logarithmic equation, life would be good. But alas, we don't. We've got this addition going on here. So what do? We need to somehow do something to this side of the equation and have just one log base 2 of, something, I don't know what that is, equals 4. If we can get to this point, we're going to be home free. Well, what do we need to do? We need to use a property that we talked about back in the day. And the property we talked about said, listen, if you're taking log any base, but we'll do log base 2 for now, of any two quantities and we're multiplying them together, this property said we can rewrite this statement right here. We can rewrite it as log base 2 of that quantity r plus log base 2 of that quantity s. Now this is a kind of confusing property, and we just kind of need to know it. We talked about it at length in our notes about why it's true. But what we're actually going to do is we're going to actually use this property in reverse right now. For instance, as it stands, we have kind of a separated logarithm, if you will. I've got log base 2 of something plus log base 2 of something else, which is very similar to what I have here. What I claim we can do is we can take this sort of expression and we condense it into a single logarithmic expression. So for instance, in our example up here, what I think we can do is we can rewrite this expression as log base 2 of, well, this quantity times this quantity. This is kind of like your r and your s from down here and down here and here. So we can write this as log base 2 of x plus 3 times x minus 3 equals 4. And we have exactly what we wanted, right? This is exactly the form we wanted to put it in. So I'm going to go ahead and drag this up here, and I'm actually going to go ahead and multiply these guys. And I think we're going to have log base 2 of x squared minus 9 equals 4. Look, we've got that single logarithmic equation now. Right? It doesn't matter in this example up here, it didn't matter what that x plus 3 was as long as it was one expression. We could have just written 2 to the 4th equals whatever this thing is. And so, in exactly the same way, we can write this as 2 to the 4th equals x squared minus 9. Check it out. And 2 to the 4th is just a number. That's 16. 16 equals x squared minus 9. And we've got a couple of options how we want to solve this. I might go ahead and add 9 to both sides. And we've got 25 equals x squared. I'm going to go ahead and I'm going to take the square root of both sides. Now we got to be careful. Remember, this means that we're going to have x equaling positive 5 or negative 5. Equivalently, if you wanted, you could have gone from here and you could have added 9 to both sides, or rather subtracted 16 from both sides. 0 equals x squared minus 25, x plus 5, and actually factored the right-hand side of it, and you get the exact same potential solutions. All right, so we've got our potential solutions, but it's always a good idea to go ahead and check and make sure. So let's try our potential solution 5. So let's check x equals 5. And when we go ahead and we plug that in, we got log base 2 of 5 plus 3 plus log base 2 of 5 minus 3. Does that indeed equal 4? Well, 5 plus 3 is 8, so I got log base 2 of 8, which is indeed 3, plus log base 2 of 2, which is indeed 1, and that definitely equals 4. So 5 is a solution. This is awesome. Let's try negative 5. We'll do this in blue, so check x equals negative 5. Well, log base 2 of negative 5 plus 3 plus log base 2 of negative 5 minus 3, does that indeed equal 4? We've got log base 2 of negative 2, and instantly we can stop and we say, wait a second. We cannot take the log of a negative number. There is no power to which we can raise 2 to and get negative 2. And so we say, nope, stop, can't do it. And so we say, you know what? Negative 5 is not a solution to this equation. And oftentimes when we have these sorts of complex logarithmic equations, we are often going to come out with 2 potential solutions, of which there will be only one. And in this case, our only solution is the number positive 5.